So hello everybody, good afternoon. We're going to recap a little bit of the dangling problems of yesterday, and then we'll go into the actual calculations and exercise matter of today. So I'm going to share my screen here. Okay. So let's go from the beginning quite swiftly through the material that we covered yesterday. Welcome. So the first time that we discussed a problem is when we had the contact line where three phases meet, in this case, the air cyclohexane-rich phase and the methanol-rich phase. They meet at a line of common contact, and the force equilibrium is governed by the interfacial tensions. So we have three interfacial tensions. We have the air liquid interfacial tension on the cyclohexane-rich phase side. And we also have the air liquid interfacial tension on the methanol-rich side. And we have, of course, the liquid-liquid interfacial tension between the two liquids. So the problem we were addressing is that given that we have a three-phase equilibrium, as depicted here in this cartoon, how do you go from this mechanical three-phase equilibrium in which the forces are indicated here by the arrows? How do you go from this star configuration to the triangle configuration that is called the Neumann triangle? The sides of the triangle are proportional to the interfacial tensions, so in fact proportional to the forces here per unit length acting on the contact line. And the angles, interestingly, are not the dihedral angles alpha hat, beta hat, gamma hat, but are actually their supplements. Now, this was a homework exercise, and we're gonna now look at the solution. So I gather you all did this very well. So what you did is you took this force factor here, and actually it matches quite well with this side of the triangle, doesn't it? Now, if we take this force factor here, put it here, and then we go to the head of this force factor, and we add, as in vector mathematics, we add this force factor here. Okay, and this one fits actually quite nicely here. And of course, its length or its magnitude is proportional to the interfacial tension. So we have now this force factor in this direction and this force factor in this direction. And of course, the remaining force factor here, we're going to put it here on this side. And so that as we go around, we're adding up these three Newtonian forces. And if there is a triangle that is closed in this way, this means automatically that the sum of these vectors must be zero. And the sides of the triangle are oriented in such a way that the dihedral angles alpha, beta, and gamma hat are retrieved here in this triangle, but the supplements actually of these angles feature in these corners of the triangle. And that you can see by carefully looking at the geometry when you displace these vectors and make the triangle. So this Neumann triangle is nothing else than a kind of abstract representation of the force equilibrium acting at a contact line. And the Neumann triangle incorporates the relationships between the forces, between the surface tensions, therefore, and the dihedral angles. Because as we discussed, these sides and angles satisfy, as in every good triangle, they satisfy the law of sines and the law of cosines. Okay. So this was this first homework there. Find out for yourselves. So you have derived the Neumann triangle from the mechanical force equilibrium. That means the zero net force on the contact line. Now, is this clear? Is this clear for you too? Yes, very clear. So when you have a question, we're going to give you the headset, because then your question will also be audible for everybody now and later. Good plan? Okay, good. So the next part of the problem that I left for homework is this one here. And it becomes more clear now what is meant by this exercise. Because suppose now we're going to reverse the inequality that describes the triangle situation. So for every good triangle, say any one of the sides is going to be less or equal in length to the sum of the other two sides, right? And equality can be reached when we collapse the triangle. But suppose now we would go further than that, and we would ask one of the sides to be larger than the sum of the other two. So what are the consequences then for the force balance and for the contact line? So the force balance, as you remember, force balance was here the sum of these three vectors adding up to the zero vector. But now suppose that one of those vectors is in length larger than the sum of the other two. Then, yeah, it's not going to close, right? The triangle is not going to close. It's not going to be, it's going to have a gap somewhere. And if it's going to have a gap somewhere, the sum of those three vectors will not add up to zero. So there will be a resultant net force. Will be a non-zero sum of those three vectors. And so there's going to be a net force on the contact line. So what will happen?
It will collapse again. So it will merge into the separate things. So your droplet in the solution will dissolve into the solution.
So this contact line will not be able to remain at rest. Period. Right? So we're going out of equilibrium. Okay, good. Yeah. So that's also solved. So for all equilibrium situations, we must have the triangle inequality. And if we would violate it, we would go out of equilibrium and the contact line would move, and maybe the droplet will spread, as you suggest, or maybe something else will happen, some other disaster. So great. So those were the homeworks, or almost all of the homeworks. Then we went into minimal density functional theory for wetting, when we started out with two phases and with one critical point and a two-phase equilibrium with a single interface between those two phases. We discussed some properties close to the bulk critical point. We discussed density difference. We discussed free energy singularity in the bulk. We also discussed the width of the interface, which turned out to be the correlation length in the system. And we also pointed out the vanishing of the interfacial tension and the critical exponent associated with this vanishing of the AB interfacial tension close to the AB critical point. Then we set out to write down functional for this interface in such a way that if we minimize the functional, we, by variational calculus, we could obtain the optimal profile of the concentration or density in the fluid or in the binary mixture. And we also could obtain the equilibrium value for that interfacial tension. So that's what we did yesterday. And we used the variational principle so that we can have the Euler-Lagrange equation for the bulk system. And we discussed that this is quite well captured in a mechanical analogy by the motion or dynamics, if you want, of a particle that is moving in what is the negative of this f function. So if the f function has a double well structure in thermodynamic significance, then the mechanical potential on which the supposed particle is moving has a double Hill profile. And the interface trajectory corresponds to a very peculiar mechanical trajectory, which is quite exceptional. And that is that you let the ball roll from one of the hilltops, giving it an infinitesimal push, let it roll down to the valley, to climb up again to the other hill, and come to rest at the other hilltop. So that mechanical trajectory, which is highly unlikely to ever happen in nature because it's highly unstable, corresponds to the equilibrium profile for the interface between two phases. Okay, and the correspondence is that m, the order parameter for the fluid, or for the easing model, if you like, corresponds to the position of the particle. X, the coordinate in space perpendicular to the interface, corresponds to time in the mechanical analogy, and minus F is the mechanical potential energy as a function of position. So then we derived that the profile is a very nice hyperbolic tangents profile, which in this case runs from minus m0 to plus m0 if we impose bulk phases with minus m0 at x is minus infinity, and the bulk phase with m equals plus m0 as the bulk phase at x is plus infinity. We could, of course, also turn it around and draw a descending profile instead of an ascending profile. We also figured out from this calculation that the width of the profile here in space corresponds to a quantity that also features this value m0, the value m0, which is indicative of the order parameter in the phase separated state. Or you could say, if you refer to the easing model, you could say the m0 refers to the spontaneous magnetization in zero external field. And so we figured out that the width of this interface is proportional to the inverse of this spontaneous magnetization value, and therefore the width of the interface will grow indefinitely as we approach the bulk critical point. So on the one hand, the interface is going to disappear because the values of m0 and minus m0 will coalesce into zero. So the density difference will vanish, but the width of the interface, on the other hand, will diverge. So there are two actually opposing trends here. And it's not at all completely trivial what will result for a combination of these two effects. And this is something that we found out by explicit calculation of the interfacial tension using variational calculus on this functional. So we calculated the Euler-Lagrange equations. Then, in order to proceed in a very swift way, we make use of the conservation of energy in the mechanical analog of this problem. And so we obtain an equation that says something like kinetic energy plus potential energy is total energy. And we can tune the potential energy so that the total energy amounts to zero. And that is then a conserved quantity all along the trajectory. If we use that in the functional, then for the optimal profiles that satisfy the Euler-Lagrange equations and the first integral, we obtained that the interfacial tension is a very simple integration over the square root of this function f. And it amounts to a constant times m0 to the power 3. So this power 3 is interesting because it tells us that the interfacial tension will vanish at criticality, and it will vanish in such a way that it goes as the spontaneous magnetization value to the power 3. Now, if we know that the spontaneous magnetization vanishes at criticality with power 1/2, something which actually I also asked you to do as a homework, and I'll come back to it in a second, then we obtain the critical exponent for the surface free energy, or for the interfacial tension, as the number 3/2. And so this simple mean field theory, which is based on the Landau-Desgen expansion of the free energy, you could say Taylor series, and is also based on the notion that only changes of the order parameter in one direction are taken into account and not in the transverse directions. So all of these simplifications in this mean field theory amount to this value 3/2 for that exponent, whereas experiments and model calculations for more realistic systems tell us that this exponent is closer to 1.3 and not 1.5. So then we arrived at a graphical construction for the interface. And this is more or less where we arrived yesterday, and I'll recap this one. So I changed the drawing a little bit in order to be more precise in correspondence with the face portrait. And so now I let the profile go from M0 to minus M0. This is actually handy, because if I do that, then I can draw the face portrait and the relevant trajectory in the upper half plane instead of in the lower half plane. So it's just a matter of aesthetics, basically. So when I draw the face portrait as minus the derivative of m with respect to space versus m, then I obtain what is called a dynamical face portrait for this problem. And this is very much in use when we discuss dynamical systems like pendula or oscillators, or by extension deterministic chaos. And so these lines, these parabolae that are drawn here in this face portrait, are like separatrices of orbits that either remain confined or that diverge all the way to infinity. And so this is like a borderline trajectory or separatrix that will take us precisely from this fixed point value, which is m0, to this one, which is minus m0. So this trajectory depicts the derivative of the profile as a function of the value of the order parameter. So we can see that if we go here from m0 to minus m0, then we have a negative derivative, and so minus the derivative is then positive, and that's why we are in the upper half plane here and not in the lower half plane. So these curves represent the first integral that we calculated, and the first integral tells us that the derivative lies on the plus or minus square root of 2f graphs. And the interface trajectory is indicated here in heavy blue line. So from now on, we're going to work with the choice of bulk conditions that at plus infinity, we have minus m0. Okay, so that's what we're going to implement from now on. And this will be hopefully consistent throughout the remainder of the presentation. So here I announced that we're going to have another little homework exercise, and so I presented it yesterday, and I hope you have done this very well. I will not go into details on this because it will take unnecessary amount of time and from our lecture. And so I just recall what was the question. The question is that we're going to calculate two exponents. One is the exponent beta for the bulk order parameter, and the other is the exponent alpha associated with the free energy singularity close to the critical point. Now, this free energy singularity close to the critical point is a very interesting quantity. It's a quantity that actually vanishes at criticality, but it is an energy per unit volume. And in order to get an energy per unit length, an energy per unit area, we need to multiply this by the characteristic length associated with the interface in the direction of inhomogeneity of the interface. And that's, of course, the width of the interface. And so here we see that the product of these two quantities, one of which is vanishing, the other is diverging, leads to a net vanishing result. So in this find out for yourselves exercise, I have given you the Taylor expansion for the free energy per unit volume as a function of the order parameter. And so we have even terms, and there is one symmetry breaking term that could in principle be present, but we're not going to have it now on this in this exercise, because we're going to work strictly at two-phase coexistence for bulk. And so we want the two minima, one at minus m0 and the other at plus m0, to have equal values for f. The only thing that we put into this exercise as a basic physical ingredient is that the coefficient of m squared should change sign as we go through the critical point. Because below the critical point, we have a double well shape, and above the critical point, we have a single well shape, because we only have one minimum there. So this is the basic ingredient on which everything is built. And the consequences of this, as you have shown in your homeworks, is that the bulk order parameter m0, which is obtained by minimizing f with respect to m and setting that derivative equal to 0. So this m0 that you get vanishes as t minus tc to the power 1/2, and the actual f itself evaluated in this m0, so when you substitute back m0 into f, you find that f goes as m0 to the power 4. And this m0 to the power 4 is very interesting because it's basically entering in the interfacial tension here as one factor, but the other factor is the width of the interface, and that we figured out went as 1 over m0. So the net result is m0 to the power 3, and that explains the exponent 3/2 for mean field approximation to the interfacial tension. So very well. So now that you survived all these homeworks, we're going to go back to the wetting problem. And that's something also we did at the very end yesterday. So let's recap it a bit. We need a third phase now, of course. We need not only alpha and beta, but also gamma phase. And the simplest approach that we can develop, at least theoretically the simplest approach, is to take an undeformable spectator phase that is not really interacting much with the remainder of the system, but just sits there as a wall. And that would already freeze one of these dihedral angles to the value pi. Now we can ask, what about the Neumann triangle in this situation? Is this a well-defined problem? How could the Neumann triangle survive when one of the angles becomes 0? Because that's what happens when one of these dihedral angles becomes pi. Well, the Neumann triangle doesn't survive, but we don't need to go exactly to the very end of that limit. We just can look asymptotically close to this situation and then pick up the relevant equation from the cosine laws or the sine laws to find the condition for mechanical equilibrium of the contact line. And as many of you know, this problem has been solved long ago by Young and Laplace in 1805. And not surprisingly, the equilibrium condition is that the force that pulls to the left here should equal the force that pulls to the right in magnitude, plus the projection of this, this inclined force vector, which corresponds to the alpha-beta interface. So the whole idea is that we look only at the horizontal components of these forces because the substrate is presumably undeformable. But still, we would like to understand how we can get to this situation starting from a Catholic, well-defined Neumann triangle, okay? So that we did yesterday. This is just, yeah. So we did that as follows. We said, okay, let's take the cosine law for the angle beta hat, and it is repeated here. And let's consider the triangle to be such that sigma alpha beta, the interfacial tension between the two liquids, so to speak, is substantially smaller in magnitude than the surface tensions of the solid against the liquid. And so we can choose either one of these two surface tensions. And in this case, we have to suppose that sigma alpha beta divided by sigma alpha gamma is a small number epsilon much smaller than unity. And we also assume all these tensions to be positive. This could be a matter of discussion, but it will take us a bit too far out of the lectures. Now here, just working to first order in epsilon, we decided yesterday at the very end of the session that we retrieve the Young Laplace equation, which says that sigma alpha gamma equals sigma beta gamma plus a small amount. The small amount can be positive or negative, depending on the sign of the cosine of beta hat. And we can establish two limits. One limit, which is called wetting by beta, when beta hat goes to 0, or the other limit, which is also a wetting situation, but we must call it wetting by alpha. Or if we talk about liquid and vapor systems, as in this cartoon here, we could also call it a drying by beta. Okay, so sorry, yeah, okay. Oh, by the way, I'm going to check if there's some activity online here. Not too much, right, at the moment? Okay. So we go back. So we could call the situation where the contact angle is 180 degrees. We could call that a drying transition, but let's call it wetting. But specify that it is wetting by alpha, not by beta. Now, now we have come to a situation where we can develop a mean field theory for wetting in the simplest possible calculation that permits one to consider three phases. Two phases that could be called live phases, and another one that could be called the dead phase or maybe the spectator phase. And so we're going to study non-wet and wet states and check whether we can induce a wetting transition depending not only on the properties of the two live phases, but also depending on the interaction between the spectator phase, the contact forces between the spectator phase and the liquid phases, right, or the fluid phases that we have. And so these contact forces and so are just, of course, as you would expect, are going to depend on the net surface tensions that are acting there. Because we're going to try to calculate all the different contributions in the Young Laplace equation. Okay, the three different interfacial tensions. But how are we going to calculate those? Well, one of them we already did, as you remember, the interfacial tension between A and B, or alpha and beta. But what about the wall surface tensions, the alpha gamma and the beta gamma? How shall we calculate those? Because we don't have a profile that extends way deep in the gamma phase, because the gamma is a hard wall. And so instead of a bulk condition for x going to minus infinity, where x is a coordinate perpendicular to the surface, we need a boundary condition at the wall, a wall boundary condition that will do the job of bringing in the properties of this gamma phase somehow, or bringing in the properties of the interaction of atoms of the gamma phase with atoms in alpha and beta phases. And for this purpose, several scientists, notably John Kahn and notably Nakanishi and Fisher, and notably De Gennes, have postulated that we could also do some kind of Taylor expansion, in which the value of the order parameter at the wall is going to be the important variable. Okay, and we call this this local order parameter, which can take some value depending on some criteria. We call this M1. So M1 is actually the value of M at x equals 0, where we put the wall. So this is our definition. Okay, so M1 is M at x equals 0. And that's where our wall is. So in the picture that we had before, here, the x coordinate for that surface tension calculation is perpendicular to the surface and is therefore vertical. Okay. We have an analogous calculation for the beta gamma surface tension, and alpha beta we already did, so that we keep in our reservoir of good results, and we'll pull it out a bit later. Okay. So again, the simplest possible way that you could think of the surface free energy calculation between the wall and some beta or alpha phases would need to be endowed with some parameters, yeah, with some kind of a parameter that would rather enhance or suppress the order parameter at the wall, and which would also affect, say, the sign of it, and that's the linear term. So that has coefficient h1, which h1 is called surface field. Is a logical term because field means you're breaking the plus minus symmetry somehow. So if we take a positive surface field, you see that the contribution to the surface free energy will be negative if we have a positive M1. So a positive surface field will promote a positive M1, and a negative surface field will promote a negative value for M1, in order to minimize the overall surface free energy. So we could say that the surface field is there to try to induce wetting or try to induce drying, either one. And then there is a second term, not completely necessary to do an elementary calculation, but very useful because the second term also permits us to distinguish between different types of wetting phenomena at a very low computational cost. And so this quadratic term, M1 squared, does not distinguish between plus or minus M1. So it's not something like a field, but it's something like an enhancement. Why an enhancement? Okay, suppose we have a positive value of G there. Then M1 would rather be non-zero than 0, right? Because it will lower the surface free energy. So it's a kind of an enhancer of the magnitude of the surface value of the order parameter. So those two terms actually will provide a very rich, at the end of the calculation, a very rich phase diagram with beautiful variety of wetting transitions and all. But we'll come to that, of course, not everything at the same time. Then the next term, we already know, because remember, there is a cost for inhomogeneity, and there is also a cost from going away from the optimal values in bulk. And so those two terms we already have discussed, but now the only difference is we don't integrate from minus infinity to plus infinity, but we integrate from the wall to plus infinity. So we have to specify also the conditions at infinity. What is the phase that we're going to choose there to set up the wetting problem? And I told you a few minutes ago that we're going to choose the minus oh, here's okay, sorry, I correct myself. I told you a few minutes ago we're going to choose the minus m0, but here I specified that I'm talking about the wall beta surface free energy. And the wall beta surface free energy is the one in which, by definition, the beta phase corresponds with plus m0 order parameter, and the alpha phase corresponds to minus m0. So likewise, I have here wall beta expression, but I could also, of course, very well have a wall alpha expression, which is analogous, but with a different boundary condition in the bulk. So when we speak about boundary conditions, we mean either bulk conditions or we mean wall boundary conditions. But we need both to solve the problem. Now, what would this look like in the Ising model for magnetism? It's a very good question, a very good point, because much of this mean field theory is just set up in the context of the Ising model and makes use of the Ising model symmetry between up and down for spins or magnetizations. This symmetry is, of course, not present in a fluid liquid vapor system or liquid-liquid system, but by suitable linear transformation, which is a bit cumbersome to make, one can map the fluid system onto an Ising model by using the correspondence that is called the lattice gas. We're not going to do that here, but we're just going to content ourselves with the insight that the physics we're going to draw from this Ising model symmetric calculation is very useful and very, representative for a class of systems to which also liquid vapor belongs and the binary liquid mixtures belong. It just makes a calculation more insightful, more simple, more transparent if we use this additional symmetry between plus and minus, and it also makes locates the critical point at the symmetric place where the external field is 0. So the external field in bulk is 0 in this model, at least for the time being, so that we can have two coexisting phases below the critical points. But the surface fields, of course, is not going to be 0 because the surface field is going to help us to get wetting. And so in this cartoon here at the bottom of the slide, I've drawn a little piece of, let's say, a two-dimensional square lattice Ising model. On every vertex or site, we put a spin plus or minus 1, and we introduce nearest neighbor interactions J in the bulk and J surface along the surface, which is here this vertical boundary here. And we also assume that there is a surface field acting on these surface spins, which tries to orient the spins along with the field. In this case, just forcing the sign of the surface spin to be the same as the sign of the surface field, unless the couplings would try to prevent that, because it's of course very well possible that we choose couplings that are anti-ferromagnetic, which we will not do here, but it's also possible that some of these spins are down, and then of course a down spin in the second column will have the tendency to also try to pull the surface spin down, but this is then counteracted by the surface field. Okay, so it's a balance of energies that will determine the signs of the spins. Now, what is the correspondence between this kind of explicit semi-infinite Ising model and the surface field here and the surface enhancement there? Well, the surface field rather directly corresponds to the surface field in the Ising model. It also has the same sign. The enhancement is more subtle. So the coefficient of this quadratic term here in this Taylor expansion in the surface order parameter does not necessarily have an immediate and direct correspondence with the with the surface coupling here, But there is an indirect correspondence in the sense that when the surface coupling, supposedly, let's take all the couplings ferromagnetic, all positive, so the spins want to be aligned in neighboring places. The surface coupling, when it is larger than a particular value, which we call the star value of the surface coupling, and this value is greater than the bulk coupling. Okay, this is also something that will be typically the case. So for such enhancement of the surface coupling, for such strengthening of the surface coupling, beyond this particular threshold value, which itself is already larger than the bulk coupling, the G in the Kahn-Landau theory, in the density functional theory, is positive. If the surface coupling is less than that threshold value, although it may still be larger than the bulk value for the couplings, but if it's less than that threshold value, then the result is that there is no surface enhancement of the other parameter, but then the G turns out to be negative. And we'll see that the sign of G is very important for the character of the wetting transitions that come out of this model, or come out of this density functional theory. Okay, so perhaps the analogy with the Ising model is not yet fully clear. Therefore, another cartoon or two will be helpful. And before I explain the cartoons, I'm going to check whether there is something that is unclear.
Yes.
Okay. I'll give you the headset.
Oh, okay. Maybe you can group
No.
one question.
No, just ask.
Okay, so in the previous,
Put on headset.
oh, can I hear?
Yeah.
But I can't hear myself.
You can speak now.
Oh, okay. So in the previous model, so the slide before,
Okay.
yes. Let me just grab my question quickly because I was busy trying to formulate something that sounded. Okay, so with this model, is it then correct to say that you have, okay, so yesterday you mentioned that 1 millimeter thickness at the interface is already considered infinity and minus infinity. And so in this part, we have, say, for on the left of the boundary would be my minus infinity, and the right of the boundary would be my plus infinity, which is why wall beta is positive m and wall alpha is negative m, correct? Am I correct in saying that?
Yes.
Okay. Okay, so then I am with you. Then for this spin, I feel like I had you and then I completely lost you. So you have the spin to be either a positive or a negative one. Is that for attraction and repulsion representation, or is that for like surface disturbance, or I did not follow for what the S would represent in this case. Okay.
Okay, good. So this is exactly the point that corresponds to the explanation of the next cartoon. Okay. So in the next cartoon, I've drawn, say, a piece of this lattice. Now, to come back to distances, if I say like 1 millimeter to the right, then you can certainly count like 1 million or maybe 1 billion of lattice sites already, because the inter-site distances here are the order of angstroms. Okay. So and to the left, of course, we're not going anywhere because we stop there at the surface. Okay. So we're not going into the solid phase or into the spectator phase at all. We're just stopping at the surface. That's where the system stops. So we're investigating the properties of what is called a semi-infinite system. Okay, system with a surface that terminates the system. So there's nothing to the left, but there's a lot to the right, and it just keeps on going to the right, all the way to infinity, which is 1 millimeter in reality, or 1 centimeter perhaps. So I've drawn a situation where we are at very low temperature, And therefore, the energy dictates what's happening in the system. There's no significant effect of entropy, because we're actually looking at lowering free energies, and in free energies, the entropy is multiplied by temperature and absolute temperature. And so close to zero absolute temperature, there's actually not going to be fluctuations, and everything is going to be perfectly ordered according to what the energy wants. And so if I have ferromagnetic coupling, so J positive, it means that all these spins want to be aligned. And in this case, they're minus, because they could have been plus, but it's either minus or plus. In principle, with equal probability, but they all have to be either all minus or all plus at zero temperature. And so at non-zero temperature, some of these minuses will be pluses, but not many. And so at very, very low temperature, this is a rather reliable representation of the system. And now, given the minus phase, okay, given the minus phase very far out to the right, all the spins have to be minuses because they all want to be aligned. But now we're going to try to pester the system a bit, and we're going to choose a positive surface field. Okay. A positive surface field, why? Because we were interested in the possibility of having the plus phase coming into the picture. Okay, and if we would be able to stimulate the plus phase from the surface outward into the bulk, we could perhaps arrive at a situation where we have a macroscopic amount of plus phase and then an interface, because ultimately very far out we impose the minus phase, and that's fixed. Okay. So having the minus phase fixed in the bulk all the way to the right, we will have to crank up the surface field to a certain strength in order to even make it possible for the surface layer to flip. Okay. Now the surface layer, if you look very well, the surface layer will flip when H1, when the value of H1 will reach some simple multiple of J. Okay. And maybe it could be just the value of J itself, right? Because J is a coupling to the next layer, and H1 is a field that acts directly on the spins, but in the same fashion that the nearest neighbor coupling will act on the spin. So with the same strength, so to speak. Okay. So if H1 and J are of the same order of magnitude, we should expect there's a conflict there. There's a conflict of interest. Okay. And the surface spin will say, yeah, I want to stay down because there's my neighbor telling me to stay down. But I also want to go up because the surface field wants me to go up. Okay. And if I crank up the surface field, I can arrive at a situation which is in the next cartoon, which is called a wet situation. And a wet situation is the surface field has convinced the surface layer to flip. Okay. And then, of course, if the surface layer has decided to stay up because there's a rather strong surface field there, then also the neighbors will follow. They also will follow because the surface spins are so determined to stay up because the surface field is sufficiently high. And then the neighbors will follow, and this has a cascade effect, you see. And the cascade effect will go all the way to the right up till some maybe a millimeter or a centimeter. But we have insisted that very, very far out, we must have and keep the minus phase. That's the setup. So we cannot have, say, plus or minus simultaneously. So somewhere there must be a break. And this break is called the interface or domain wall. Okay. And now you can ask, yes, but what is the shape of that domain wall? Is it sort of very wiggly and very irregular? Well, it depends on temperature. If temperature is very low, then energy has all that there is to say in the system. and the energy will prefer to have the least possible number of broken bonds, because every broken bond will cost an energy 2J. And so at very low temperature, this interface will be almost like linear planar, and that's what I've tried to sketch there. And so this is the wet state in the model calculation, where you actually say impose always the same phase in bulk, but you allow for the possibility that that the other phase, the converse phase, will intrude between the wall and your interface that you will necessarily have to put there in order to be able to go back to the minus phase, because that's fixed. Okay. So these are the two possibilities, the non-wet and the wet possibility. And the calculation will tell us where the transition is, which value of the surface field will make it, as a function of temperature also, if we extend the calculation to non-zero temperature. But at zero temperature, you can imagine that the conditions will be very simple, okay? And that there will be no temperature dependence and no complicated dependence on couplings. So this is the cartoon which distinguishes the three actors of our Young-Laplace equation. So I go back here. So in this cartoon features a wall minus interface. In the next cartoon feature a wall plus interface and a plus minus interface. If we are able to calculate those three quantities in as simple geometry as possible, even with only an inhomogeneity in one spatial coordinate, so no contact angle, whatever considerations in the picture, if we can calculate those three interfacial tensions, test Young's law, we can obtain the cosine of the contact angle that would be there if we have all three phases in a contact line geometry. You see? So this is a big trick. See, we can get the ingredients for the Young-Laplace equation from calculations in which there is only a one-directional inhomogeneity. We don't need to calculate these free energies in a configuration with a contact line. We can afford having no contact line and having just the three, say, surface tension calculations far away from any contact line, just the surface calculations, and then putting them in the Young-Laplace equation and extracting the cosine of the thermodynamic contact angle that is not even present in the geometrical setup that we have used to calculate the interfacial tensions. So that's a big trick, okay?
So right in the beginning of yesterday's lesson, when we spoke about wetting and the collapse of the three phase lines into the two separate bands, the three separate bands, can we also then assume like this would be the three separate bands with the alpha, gamma, and the beta then? And because of that, we can then get the cosine angle that we would put into the equation then.
Yeah, so let's go to this picture now. Let's go back to this. Let's go back to this picture now. So here we have a realistic situation with the three phases present and the three-phase contact line, okay? But what we're saying is that in order to calculate this gentleman here, okay, we can just as well have the gamma phase and then the alpha phase in bulk, okay? And we calculate this contribution. Now to get this one here, we go far away to the right and we just calculate the gamma beta interfacial tension, okay? In a setup where the bulk phase is beta and the wall is just gamma, okay? And the alpha beta interfacial tension, we calculated already separately in a configuration where minus infinity is the alpha phase and plus infinity is the beta phase. So the x-coordinate for this calculation, so the x-coordinate for this calculation is actually coordinate perpendicular to that interface, but very far out, say very far from any other phase, without any gamma phase in the picture. Okay, so this one is calculated without a beta phase in the picture. This one is calculated without alpha phase, and this one is calculated without the gamma phase. And then we put them all together in Young's equation, which is this one here, okay? And extract the cosine of beta hat just algebraically. And then see whether it's going to go to unity or -1, okay? And under which conditions. And that we call the wetting transition. So that's the game. Good. Yeah, good. Okay. So here we go back to our simple density functional theory, which features two phases in bulk, plus and minus, and also features a surface field and a surface enhancement, and the surface value of the order parameter. Okay. Now, this problem already is a beautiful variational calculational problem, because there are two ingredients here. One ingredient we already explored in detail, and that is to vary the functional with respect to the order parameter. And so the variation of the functional with respect to the function that's being integrated over is giving us the Euler-Lagrange equations. Okay, so that we did, and I have actually explicitly included the derivation of the Euler-Lagrange equations here in this calculation. That's one ingredient. And if you look at the top of the slide, the Euler-Lagrange equations are obtained by requiring the functional to be extremal with respect to variations of m, which is a function here in the functional. And so we change m into m plus delta m, and we go to first order in delta m, and we require that that first variation be 0, and that gives us the Euler-Lagrange equations. That's how it works. But there is another ingredient here. There's not only m of x, but there's also this wall value m1, which we may consider to be an independent quantity, which could be fixed. And then we could derive properties of that problem with fixed wall value. We could still obtain the Euler-Lagrange equations and everything. Or we could also allow that value of the surface value of m, we could allow that one also to be variable, and to see whether we can get conditions for extremality with respect to variations of that value as well. And so we can let m1 go to m1 plus delta m1, and go to first order in delta m1, and require that the coefficient of delta m1 then vanishes, and see what kind of equation that would be. And that will give us the boundary condition. The result of that calculation gives us the wall boundary condition, okay, on the profile. So that's an additional criterion to find the optimal order parameter profile. So we find the differential equation that it must satisfy, and we also obtain, say, two boundary conditions, one in bulk, and we have chosen it to be the minus phase in bulk, but also the wall boundary condition can also be used to obtain the optimal profile. Or you could say, and this is of course a very important conceptual conceptual step, you could say, let's do this in two in two stages. Let's first pretend we fix the wall value, and then obtain the optimal surface free energy using the Euler-Lagrange equations for the profile that satisfies the bulk boundary condition. Okay, with fixed wall condition. And then we get a function of the wall value. because the wall value was some given value, but as a function of that given value, we can plot our result. Okay? We can calculate for arbitrary surface value fixed, and then plot the free energy as a function of that chosen fixed wall value. Then in the next step, we use the wall value as a variable. Okay. So first we compute the surface free energy for every possible fixed value of the wall parameter, or wall order parameter, and then we plot that function. We plot the result. No. The surface free energy can be obtained for a given M1. Okay? For a given M1. But you can choose any M1 that you want. So you plot the result as a function of M1. Okay? And then you check whether that function maybe has minima. Okay? Yeah, M1 is the wall value, right?
Yes, but I'm saying, is it this because we take N1 to be an M1 that we then take to N1 plus delta over N1? Then that delta over N1 is what we vary.
No.
Oh gosh, I'm so lost there.
No, I start again. The variational calculation consists of two variations.
Yes.
But you can also say, I don't want to do these two variations simultaneously. I want to do one, and then I want to do the other. Okay? So if you only do the first one, if you only do this m goes to m plus delta m, and you keep m1 fixed, so you don't let m1 go to m1 plus delta m1, but you keep m1 fixed, and you call that fixed value m1, you get a result that depends on m1. And you plot that result as a function of m1, and you look at it. Okay? Then you have not imposed the variation of m1 into m1 plus delta m1. You've not done that. Okay? So that's what we're going to look at. Okay, so let's do the two variations simultaneously now. Okay? The hard way. Okay? The result is that the variation of the functional is this expression. Okay, these are proportional to delta m1. And then this is the integral. And in the integral, I have replaced m by m plus delta m. Okay, and this is the derivative of it. And here I have subtracted the integrand, say the original integrand in which I had m and not m plus delta m, because I want to have the variation of the functional, the difference with respect to the previous original one without variation. And then the last one is also proportional to delta m, because that's this df dm, okay? Because there's this function f. And if you have the function f, you just vary it, you have df dm times delta m. Okay? So then, as some of you know by variational calculus, you can further work this out. So the derivative ddx of delta m is the variation of the derivative. Okay, that's standard. You integrate by parts, and you keep track of the fact that the delta m at the wall is just delta m1. Okay, and that delta m in bulk is 0 because the bulk value is fixed to either plus or minus m0. Okay. And then the result is that the variation of the functional has these two contributions. So one is proportional to delta m1, and the other is proportional to the variation of delta m, which is a function and therefore occurs inside the integral. Now, if this quantity must be 0 for arbitrary variations of the profile and for arbitrary variations of the wall value, there is only one possibility, and that is that this coefficient vanishes, okay? and that this integrand, the function that multiplies the delta m, also vanishes. Because otherwise, it will not be true that for any chosen arbitrary function delta m, that integral be 0. Okay? You can choose the delta m to be an arbitrary function, arbitrary small function, but you can choose it to be anything you like. Okay? And if this integral of this delta m multiplied by this function, whatever it is, must always be 0 for any choice that you make for this delta m, the only possibility is that the thing between brackets must be 0. Okay? And that gives you the Euler-Lagrange equation, which we already knew. But the first one, the coefficient here vanishing, coefficient of delta m1 vanishing, gives us the wall boundary condition. Okay? And that tells us that there is a relationship between the derivative of the profile at the wall and the surface field and the surface enhancement and the value of the profile at the wall. Okay? So that relationship, that equation is a boundary condition that relates the derivative to the function at the wall. So what I said before is that we can postpone this wall boundary condition business and we can keep M1 fixed. Okay? If we keep M1 fixed, then this last line will not have this first term because there is no delta M1. Okay? And so we don't have a wall boundary condition yet. We don't have it yet. Okay, but we can look at the functional, at the surface free energy for a given value of M1 and then plot that result as a function of M1 and then look whether that perhaps has minima. Okay, and the places where that function has minima might well correspond to the solutions of that boundary equation. They might well. They need not necessarily always correspond because this boundary condition is derived by assuming that we can have a small infinitesimal change of M1, okay, and that the resulting function be extremal with respect to M1, okay, when this coefficient vanishes. Okay, you see? So this is like requiring a derivative to vanish. But this may not necessarily give us all the interesting minima, because we could have a boundary minimum at some value of M1. No, we don't have this here, but we might have a situation with a boundary minimum where perhaps the physical interval for M1 is limited between two values like say C and D, okay, and then the free energy could have a boundary minimum at C perhaps, where the slope is not 0. You see, because there could be physical boundary, yeah, of the values of M1. So minima that might occur at places where the slope doesn't vanish are possible in principle. They're called boundary minima, okay? And we could not catch them. We cannot catch them by asking the first variation to vanish because the derivative is not 0 there, okay? The same holds for the Euler-Lagrange equation. The Euler-Lagrange equation tracks minima in function space, but internal minima, also does not take into account any sort of boundary minima that could exist in function space. So to rely on the vanishing of the first variation in order to find the minimum is a dangerous game. We can get burnt, okay? But it's a very good first step in this problem. Okay, and we can tell in hindsight, we can tell whether we should have been more careful or not by looking at the minima and check that they're internal minima and not boundary minima. Okay, that we can see later.
But this is a boundary minimum.
No,
Not infinite.
the term boundary minimum that I've used in the last 3 minutes or 4 minutes has nothing to do whatsoever with the wall boundary here
Okay.
in this system.
Okay.
Okay, it's a different significance of boundary, of the use of the word boundary. Okay. Okay, so boundary minimum means a minimum at the extremity of the range of values of a certain parameter. Okay. Okay, good, cool. So now that we have this, when we have worked very hard to get this, we can do the following. You do remember our face portrait, okay? Minus m dot versus m. And you also remember, maybe vaguely, that these two parabolae correspond to the plus or minus square root of 2f. And so these two parabolae tell us that the trajectories satisfy the constant of the motion, satisfy the first integral of the Euler-Lagrange equations. Okay, good. So if we want to stay on these parabola, it's fine. We will satisfy the Euler-Lagrange equations, but we do not necessarily satisfy the wall boundary condition. But the wall boundary condition is rather simple. If we look at it again, here say, look, this is a linear function of m1, and this is the derivative evaluated at the wall, okay? But the face portrait features this very derivative versus the function. So if the derivative is going to be linear function of the variable, the representation, the graphical representation is a straight line. And that straight line that is drawn there, a little bit inclined, is this h1 plus g times m divided by some constant. So if we want to satisfy simultaneously, this is an option that we can take, the Euler-Lagrange equations and the wall boundary condition, then we must stay on these parabolae and we must start from a point that is some intersection of the straight line with these parabolae. Okay? So if we do that, we would obtain an optimal profile that satisfies the wall boundary condition and hopefully also the bulk boundary condition. But if we want to satisfy the bulk boundary condition, we must not specify it carefully. If we want to satisfy the minus m0 bulk boundary condition, then we must follow the leftmost heavily colored trajectory. If we want to satisfy the bulk condition that m is m0, then we must use the rightmost heavy colored trajectory, starting from the intersection of the straight line with the parabolae. Okay. So here we already get a flavor of how to get the optimal profiles for the wall plus and for the wall minus order parameter profiles. Okay. Yeah. Now you see that I've marked two pieces of these parabolae as unphysical. Okay. Why is that? Well, if you look at them, you see minus m dot is minus the derivative of m. Okay. So if we want to stay on these parabolae, that means we want to satisfy the Euler-Lagrange equations and the first integral of them. Then in the upper half of this picture, okay, the upper half plane, we must follow the arrows from right to left, okay, because in the upper half plane, minus m dot is positive. So m dot is negative. So m must be decreasing as we go forward in time or in space, okay? So remember that space is time in the mechanical analogy. So in the upper half plane, the arrows go from the right to the left, okay, necessarily. In the lower half plane, minus m dot is negative, so m is increasing. And so we must follow these parabolae according to the arrows which go from the left to the right, okay? But we must necessarily end up either at minus m0 or at plus m0 at infinity, right, in the bulk. So these two pieces that are marked unphysical, they are not part of our problem because they will drive us to all the way to infinity, okay? They will not provide trajectories that end up either in m0 or in minus m0, okay? So these two pieces have to be thrown away. And so we are left with this part here, and we are left with this part here. And the wall boundary condition is a straight line, as we have determined, which may or may not have intersections with these parabolic curves. Notably, the wall plus or minus surface free energy, which is written down here, takes the following form: minus h1 m1, we know that, minus g m1 squared over 2, we know that. And then comes the integral, which, making use of the Euler-Lagrange equations in the first integral, can be written as integral from plus or minus m0 to m1 of this square root of 2f function as a function of m. Now, here I've been rather careful here, because in this picture, if I look at the wall plus surface free energy, that is obtained from this rightmost heavily colored profile. And as you can see, m0 is less than m1. I have not indicated m1, but m1 is the value of m that corresponds to the intersection. So the order of the limits, of the integration is correct. Plus m0 at the bottom and m1 at the top. Similarly, for the other one, minus m0 is the bulk value that is reached. So this is the wall minus surface free energy. And m1 is also greater. The m1 is this intersection point, projected down to the m-axis, this value. And so this value also exceeds minus m0. So also the order of the limits in the integration is correct in this way. Yeah. The order of the integrations from m0 to m1 or m1 to m0, whatever, must always respect the property that the integral must be positive. Because the integral is a sum of a gradient squared and the f function, both of which are always positive or zero. Yeah, never negative. So I must always arrange the order of limits of integration here carefully, so that the resulting contribution is always positive. You mean if we would start from where? Can you? Oh, that one there. That one there. If we start from this okay. So your question now is a beautiful one, because you're asking me about this intersection, which I did not discuss yet. So that's of course a beautiful question, but we can start anywhere we want, you know. We can start anywhere we want on these parabolae. We will still satisfy the Euler-Lagrange equations. We will not necessarily be optimal with respect to the possible choice of wall value. But we may not care too much in a first step. Okay. So suppose we start from this intersection, then we would go look at my arrow. We would go like this, right? Oops, sorry. And right. So back. So we follow this down to here, and we would end up in minus m0. So that would be perfectly fine. A wall minus profile may not be optimal. As it turns out, it's actually local maximum. It provides a local maximum of the surface free energy. So it also satisfies the property that the first variation is zero, that the derivative is zero with respect to wall value, but in this case it's a maximum. Okay, so that's we will see this maximum in a moment. But I repeat, we could start from anywhere. We could also start from here. Look at my arrow. We could start from here and then go to plus m0. Okay, but then we would have to integrate from m1 to m0 of the square root of 2f. Okay, because we must have a positive contribution always. Okay, but that would be perfectly fine. It would maybe not be optimal. The sigma plus minus is the alpha beta interfacial tension, and we know that that it takes this value from a previous calculation. Okay, so here we are on the brink of obtaining the three constituents needed in the Young-Laplace equation to determine the cosine of the thermodynamic contact angle. Okay, so we have the three ingredients. We just have to do the calculations for all possible starting points here that we may consider. The boundary condition, the wall boundary condition, helps us to select extrema, maybe minimum, maybe maximum. Maximum, very bad news because it's the worst we can do. But minimum, of course, is physically very interesting and could be candidate for the true physical profile. So the wetting condition for zero contact angle in this case would be that the wall minus tension equals the wall plus tension plus this plus minus tension. Okay. So coming back to this picture here, you see, this picture is the wet solution. So there's the wall plus the plus minus equals the wall minus, equals the wall minus. So that's now in this phase portrait, the condition for wetting amounts to an equal areas rule. So there is a geometrical or graphical interpretation. And that's the next slide. See? Now I'll let you look at it a little bit before we discuss it. There's a small change in notation that shouldn't disturb you too much. The L corresponds to plus M0 and the G corresponds to minus M0. It comes from literature where the L is liquid and G is gas. Okay, and you see minus m dot versus m. You see the arrows. You see that I've deleted the tracks that are leading into the abyss, right? That will take us nowhere. And so all the useful tracks are indicated. The wall boundary condition is indicated. By the way, I've chosen this line here to be perfectly horizontal. What does that mean, Jane? What does that mean for H1 and G? Yeah. It's an accidental choice. It's not. It's.
H1 is the surface field, and then the G is the extended field. And so if it's flat, it means that the extended field should have not much of a contribution towards the surface field.
Yeah. So G is 0. Yeah, you got that. G is 0. The slope is 0 of this straight line, and so this is an accidental choice. To G equals 0. It's not representative, but it's just you know, just could be anywhere near 0 would give the same result. The upshot of this plot is that if we do the variational problem in 2 steps. So first we care about Euler-Lagrange equation. We stay on these parabolae, okay? But we don't care about starting point. We consider all possible starting points. And we plot the resulting surface free energy. Then this branch here corresponds to trajectories here that do this. Look, you can start here, for example. I go here, and then I go to minus m0, okay? And I count how much that costs. And that I plot here. That's this value, okay? Okay, now I start somewhere here, okay? First I go to the liquid fixed points. So go from the wall to the liquid phase. And then I go from the liquid to the gas phase, because we ultimately must always end up in the gas phase in this calculation. And the cost of that surface free energy contribution I put here is this value here, okay? Is this value here. Then you'll say, well, excuse me, I prefer to start here, or maybe let's say here, okay? Prefer to start here. Good, then you have to go this way to the liquid, and then you can go to the gas. How much does that cost? Okay, that costs this much here, okay? And then you say, yes, but actually I want to be a bit more physical. I want to start somewhere maybe here. Okay, then you go directly to the gas phase. How much does that cost? This much. This much. See? Or, well, I want to start here rather, and then I want to go to the gas phase like this. How much does that cost? Well, that costs this much. Okay? And so these are the costs of surface free energy for any possible reasonable trajectory that will ultimately end up here. And that starts from anywhere that you want. Okay. So this is what I wanted to tell you when I was speaking about fixing the wall value. And not caring whether it gives a minimum or maximum or whatever. Okay. Fixing the wall value, and for that fixed wall value, I calculate the cost. And I plot that as a function of that fixed wall value. That's what we have here below. Now note that this result is not, mathematically, is not a function, because it's multivalued. It's multivalued. What is the value of this function here in m1 equals 0? Well, there are two. What is the value here? There are two, right? Here maybe there's only one. Okay, fine. But in general, there's more than one. And so this result of doing just the bulk minimization, not the surface minimization, gives you a multivalued function, which is not a function mathematically. Okay. And for a multivalued function, you must be very careful, because as we will see shortly, for a multivalued function between two minima, there need not be a maximum in between. There need not be. There may be, but there need not be. But here we see that in this branch, there is a minimum here, maximum here, and a minimum here. Now, not surprisingly, the minimum here corresponds to the intersection of the wall boundary condition curve and the Lagrange, okay, and the first integral. Not surprisingly, the minimum here corresponds to the intersection of the wall boundary condition and the parabolae. And also, not very surprisingly, this extremum, which is a maximum here, corresponds also to an intersection there. Okay, but these outer intersections are physically much more interesting than the inner one. The inner one is actually one of the worst possible cases. Not actually the very worst possible, because the very worst possible, starting from this m1 value, the very worst possible that will still satisfy everything else is this here, which is what happens when you start here and go here first and then go there. Okay. So the maximum is not even the worst, but it's only maximum on one branch. And this is a multivalued function. But the multivalued function with different branches helps us to understand which are the physically more interesting solutions. Okay. Now, an exercise that you could do is to check whether the in the expression for the surface free energy, the different terms can all be interpreted as integrals. Can all be interpreted as integrals under the curves here in the phase portrait. Some are integrals under the square root of 2f, okay? And some are integrals under the straight line. Because remember, it's h1 times m1 and g plus gm1 squared, which is the integral of h1 plus gm, okay? And so the exact condition you can work out in your free time, that the exact condition for these two minima here below to have equal values of surface free energy, so the condition for those two minima to be equal, is that these two areas are equal in this phase portrait. Yeah, it's surprisingly, no? So the equal area rule gives you the equality of these two minima, which means that the solution that goes directly from the wall to the liquid has the same surface free energy. The solution that goes directly from the wall to the liquid, plus then from the liquid to the gas, has the same surface free energy as a solution that goes directly here to the gas phase. From this wall value, okay? From this wall value here. So this solution will make the Neumann triangle collapse. Okay, and we'll have the cosine of beta hat equal to unity. So that's the wetting transition. So the cosine of beta will become unity when these two areas are equal. And then you will say, okay, what happens when these two areas are almost equal but not quite equal? Well, then you're not quite at the wetting transition, but you could be on either side of it. You could be on the side where you have a Neumann triangle, or you could supersede it. You could sort of break it, you know, pull it apart, so that one side of the triangle is actually greater than the sum of the other two. It's also possible in this construction. It would just mean that that one of these areas would be larger than the other one, or would be smaller than the other one. So you can go on either side of the transition. Now, if you go into the wet state and you break the triangle, then you go into what is called a non-equilibrium, non-equilibrium state. Okay, but you can evaluate the surface free energy in this density functional theory. You can evaluate the surface free energy of that metastable state. As in many mean field theories, you can evaluate the cost of those metastable configurations, which are not stable, but metastable. Okay, so they would still correspond to some local minimum, but not the minimum. Okay, so this calculation also allows one to explore perhaps unphysical or perhaps forced, mathematically forced metastable states, which may not exist in reality, but which do exist in this type of theories. So there's more flexibility here than in the Neumann triangle. Okay, so all physical states of the Neumann triangle are represented, but as I already explained, the Neumann triangle here is actually taken into limits where two sides are very long and one side is very short. Okay, because we have an undeformable wall. Okay, but we can still speak asymptotically. We can still speak about the Neumann triangle. But even states that are outside the Neumann triangle description can be captured by this calculation, at least mathematically speaking. They need not be physically realizable. So, so this is the first order wetting transition. Why is it the first order wetting transition? Because we actually we experience here a jump in the surface order parameter value. From one minimum to the other minimum, the order parameter at the wall jumps. And so we have a kind of an abrupt change of of configuration in equilibrium between the non-wet, between the asymptotically, say, non-wet and the wet state. Okay, and so this this jump represents, say, if we do the surface free energy calculation in a little bit more detail, as we will see in a moment, this jump represents a jump in the first derivative of the surface free energy with respect to, for example, temperature, or with respect to, for example, the surface field. Okay. So you can imagine that changing the surface field will change the location of the wetting transition. Also changing temperature, because if you change temperature, go closer to the critical point, then these parabolae will become more and more, say, the area, the eye, as I may call it, the eye here in this overlap of these two parabolae, the eye will shrink as I go to the bulk critical point, because M0 goes to 0. Because M0 goes to 0. Okay? And L is M0 and G is minus M0. So now, I already explained in rather energetic terms, if I may say so, this use of this constrained surface free energy, right, where you fix the wall value. So I've repeated it here, and we have explored everything that's on this side, because we have used this auxiliary multivalued function to help us find the local minima of the surface free energy, given that we must end up at minus M0 for all possible profiles. Okay. So the wetting problem you could summarize as follows. So you choose the bulk to be at minus M0, okay? But the wall, you give it a positive surface field. So you kind of frustrate the system. But then you ask, okay, is this amount of frustration strong enough, large enough to have the plus phase intrude between the wall and the minus phase? Or will it just frustrate the minus phase at the wall and pull it up a bit, and that's it? See? So you frustrate the bulk condition by manipulating the surface, and you ask when will this frustration be strong enough to really convert the minus phase to plus phase near the wall, and then have a plus minus interface very far out in order to end up in the minus phase anyhow, you see. So the wetting problem is a kind of a question of loss and gain, right? So you gain at the wall by pulling it up all the way up to the plus phase, but you must then pay the extra interface, because you must eventually go back to the minus phase. Okay. So here, look here. We still have a few minutes. We're going to stop a bit earlier, like 3:45 today. This is what happens if you choose this G. You know, if you choose G to be strongly negative, okay, large and negative, you get a very steep straight line there. That is the wall boundary condition, and your auxiliary function will look like here below. You will still recognize the two branches, so it's still multi-valued, okay? The orange branch corresponds to all solutions that start here from this orange segment. The yellow values are all the surface free energy values that result when you start from the yellow segment. There's an intersection here with the wall boundary condition. This is of course indicative of a minimum, okay? There's another intersection here, which is indicative of another minimum, okay? And that's it. And here's a junction. Here's a junction point. It corresponds to plus M0, okay? Junction of the two branches. But you see, you have a local minimum here and another absolute minimum here. So these are two minima of this auxiliary function, or I should say multi-valued auxiliary function, as a function of m, okay? Actually m1, so this should be m1 to be more precise. But I have two minima, two neighboring minima here without maximum in between, right? You agree? So that's because of the multi-valuedness that this is possible. And this absolute minimum is the physical solution here that corresponds to this profile. Now look, because I start here quite close to m0, I start with a small absolute value of the derivative. So I can go pretty far out before I cross here and go to the minus m0. See? And I can push that crossing value L, that's a distance from the wall, I can push that farther and farther and farther away from the wall if I let this point and this line move slightly to the right and let this point approach the bulk point. And if I do that, I obtain wetting condition in a continuous fashion, not with a jump. Not as a jump between two solutions that are very distinct. No, as a gradual approach of a single solution to its limiting wet state solution. Okay? And this phenomenon, if I let this happen, or if I change temperature and let M0 come in until it hits the line there, I will push L out to infinity continuously, and this is called a continuous or critical wetting transition instead of a first order wetting transition. Okay.
But this is now with the slope being constant, the gradient of the slope being constant.
Yeah, or this is with this very sloping. So with the G that is negative and large enough in magnitude, I will get this solution as my equilibrium solution. And I can push the solution towards M0, at which point I have the wetting transition. Okay. And this just by virtue of the fact that this point approaches this plus M0 point. Okay. So then this gets longer and longer and longer, right? Because the derivative is very small. Okay, this is the derivative, and so it's my mechanical ball just near the hilltop and just slowly coming to a finite velocity and then going. Okay, so this is critical wetting. So this theory can give us first order wetting. Okay, when this competes with this solution, or can give us critical wetting, but there's only one physical solution that gradually can be pushed all the way to the wetting state. And the plus phase intrudes completely and the interface is pushed all the way out. And yeah, this is what I'm going to do. I'm going to leave it to this today. And so we've worked very hard, so we need now a good rest, and therefore we need also holiday, which is tomorrow. And it's Women's Day in South Africa. Good. And we'll meet the day after Women's Day, and we'll go on a little bit with this, and then we'll go to another exciting chapter in the surface and interface, phase transitions, and with critical phenomena. So let's see. Just check if there's some problems online. No, everybody's happy. Good. So see you soon. See you soon again. And